Hello everyone, Professor Macon. I am almost Dr. Macon. I'm going to go ahead and lie. I'm Dr. Macon coming at you live. And in this video we're going to talk about Taylor series. So this typically would be the end of a conversation on series. We've already talked about power series in a prior video. And what we're going to do here is we're going to look at what we call a Taylor, or sometimes we look at a special case, the Maclaurin series. Alright, so in general, power series we would write in the following manner. So in the past, we've talked about writing function in terms of what we would call an infinite polynomial. Right? And we're going to look at powers of x. So when we're looking at a power series, right, we're typically considering a function, and it could be any function, right? The function could be sine x, function could be e to the x, function could be 1 over 1 minus x, right? It could be any function we want. And in particular, we write it in an arbitrary fashion. We'd say here's the zeroth coefficient, right? That's the constant term. And then we'd have c1 times x minus a to the first power, c2 x minus a to the second power. I'm running out of room here. Let's say c3 x minus a cubed. And, we would have a fourth degree term. And plus dot dot dot. So this would be an infinite series. Okay. Now, technically, if I write that in sigma notation, right, I'm talking about, I have c sub n x minus a to the n, as n goes from 0 to infinity. Right? So there would be my closed form. All right, so the question here really is, how do I find the coefficients? How do I find c sub 0? How do I find c sub 1? How do I find c sub 2, c3, c4, so on and so forth? Now, the reality is those coefficients are going to actually determine the function that the series represents. All right, so I'm looking at Stewart's calculus book, and just want to point out to you, for the function 1 over 1 minus x, this is the power series that we would get. And we'll notice that the coefficients are all 1x, 1x squared, 1x cubed. So you can see over here the coefficient being 1, and then I have powers of x. So when the coefficient is 1, I'm getting the function 1 over 1 minus x. Now, if we look at this example here, the function that we're representing, I want you to ignore the stuff in the middle, it has nothing to do with our conversation. The function we're looking at here is 1 over 2 plus x. So to generate this function, the coefficients we get are these guys, right? So negative 1 to the n over 2 to the n plus 1 power. So I don't have coefficients of 1 for every term. I have these coefficients, whatever they would spell out for me. If I were to look at another example, the function x cubed over x plus 2 would have these coefficients. So they're slightly different than the ones we just looked at. Right? And we would be looking at negative 1 to the n minus 1 over 2 to the power of n minus 2. So when these are my coefficients, this is the function that I am getting. So our question in chapter 11 in Stewart's book here, right? The question is, with the Taylor series, we're asking, what are those coefficients? How do we find those coefficients? So here's how we would typically derive the formula that we're going to use to find those coefficients. Oops, that's the wrong thing. I want my Word doc. All right, so I need to find those coefficients, C1, C0, C1, C2, so on and so forth. So in order to do that, we're going to specify a couple things. Right? So what we would want is for this function to equal itself in all possible scenarios. So in other words, I would want the function to equal itself. I would want the derivative of the function to equal the derivative of the series. Right? I would want the second derivative of the function to equal the second derivative of the series, so on and so forth. I would want the third derivative of the function to equal the third derivative of the series. So if these two things are to be equal, right? If I'm supposed to have the function equal to this infinite polynomial, if you will, right, the power series, then I need the derivatives to equal, so on and so forth. Now, something I didn't mention when we first started this, the series is centered at A. That's what we would call the center of the series. And I'm going to come back to that in a couple minutes, and we're going to talk about what that really means. We'll look at a graph. Right? But what we're going to do is plug in the A value, and we're going to center the function where the series is centered. So in other words, if I plug in A to my function, what I have is, f at A. And then if I plug A up here into my power series, notice what's going to happen. I'm going to get A minus A, which is 0. I'm going to get A minus A squared, which is 0. A minus A cubed, which is 0. So all these terms are going to zero out. And all I get is the first constant, the first coefficient. Right? The x to the 0 coefficient. So I'm going to come over here and I'm going to say what we have then really is the 0th coefficient is the derivative at A. Right? All right, so how would we find the next coefficient? How would we find C1? So what we're actually going to do then is take the derivative and set it equal to the derivative of that polynomial. Right? So what we're going to do now is we're going to have f prime. We're going to have f prime at A. So first of all, let me come back for a second. What is f prime at x for my series? I want to look at f prime at x for my series. So what is f prime? So I'm going to come back up to this polynomial, our power series. If I take the derivative of the constant, it is 0. If I take the derivative of this linear term, it's C1. If I take the derivative of this quadratic, I'm going to bring the 2 down, take 1 away. I'm going to take the derivative of the cubic. I'm going to bring the 3 down, take 1 away. And then, if I take the derivative of this term, same thing. I'm going to bring the 4 down. And that's supposed to be a C there, right? Let me fix that so that doesn't look confusing. So there's the derivative. And I want the derivative and the function to be equal. I want the derivative of the power series and the derivative of the function to be equal. So I'm going to plug A in. I'm going to plug in the center. And so what I'm going to get in this case, notice that when I plug A into this term, it's 0. When I plug A into this term, it's 0. When I plug A into this term, it's 0. So I found out that C1 is the derivative of the function at A. So C1 I can find by taking the derivative of the function and plugging in the center. So let's keep doing this a couple more times. So I want the second derivative of the function to equal the second derivative of the series, the infinite polynomial. So let me scroll down a little bit here. So I want to find the second derivative. So I want to find, here's the first derivative, let's find the second derivative. Let me go back to blue. Right? Let's find the second derivative. Right? So what is the second derivative of my function at x, right? So the derivative of C1 would be 0. The derivative of this linear expression would be 2C2. The derivative of this quadratic, I would bring the 2 down, and I would have 3 times 2 C3. That's a C3. X minus A to the first power. My writing is sloppy today, forgive me. If I take the derivative of the next term, taking the derivative of this expression, right, I'm going to bring the 3 down. So I'm going to have 4 times 3 c sub 4 x minus a squared, right, plus dot, 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 right. So if I plug a into that expression, right, excuse me, what is f double prime at a? So if I plug the center into that expression, again, really similar to what we've done the prior 2 times, this term is going to zero out. A minus a is 0. A minus a squared is 0. So all we're going to end up with is 2c2. So c2 is half of f double prime at a. And notice we're kind of getting a pattern here. Notice that the C1 coefficient is the first derivative, and the C2 coefficient is the second derivative. Now it kind of looks like I'm dividing the second derivative by the order of the derivative. So this is the second derivative I've divided by 2. This is the first derivative, I've technically divided by 1 here. So it looks like we might be getting a pattern here. Let's continue a couple more times and let's see if that pattern really fits. So let's find the third derivative. We want the third derivative of the function to equal the third derivative of that infinite polynomial. So come back here. Excuse me. My allergies are killing me today. So I got f double prime of x, and that is going to be, so if I take the derivative of, excuse me, I already did f double prime. We're doing the third derivative. We want the third derivatives to be equal. So the derivative of this constant is 0. The derivative of this term is linear, right? So it's just the coefficient, 3 times 2 times c3. And then when I differentiate the squared term here, the 2 comes in front. So I get 4 times 3 times 2, and then I get x minus a to the first. Now think about what the next term would be. Right? Oh, goodness, I forgot in that term the c sub 4. Right? This is c sub 4 here. I forgot that guy. Let me come back and put him in. Right? And that would be, bring the 2 down, take 1 away. That would be to the first power. Now let's think about what the next term would be. Right? The next term would have come from the cubic. Right? And the cubic would have actually come from the 4th degree on the prior term and the 5th degree on the term before that. So we can kind of see the pattern, right? C sub 3 starts with 3. C sub 4 starts with 4. So we're going to have 5 times 4 times 3. And I'm going to have c sub 5 x minus a squared. That would be my next term, plus dot, dot, dot. Right? So if I plug a into the third derivative, right, we're going to start to see the same thing here, right? So this expression, a minus a to the first, will become 0. X minus a squared will become 0. So I'm really just getting 3 times 2 times c3. So my c3 is really what? My c3 I'm going to divide over the 6. But before I actually divide over the 6, I'm going to point out that that's 3 factorial, right? This is really 3 times 2 times 1, which is 3 factorial. Now if we come back up here for a moment and we look at this guy, right? Look at the x minus a to the first. That's really 4 factorial. 4 times 3 times 2 times 1. If we look at the squared term, this is almost 5 factorial, right? It's 4 times 3, 5 times 4 times 3. Now when we take the derivative of this, the 2 comes down, and I really get 5, 4, 3, 2 times 1, which is 5 factorial. So we're seeing a pattern. Really up here, this was a 2 factorial in the denominator. Right, really right here, this is a 1 factorial in the denominator. So C1 has the first derivative over 1 factorial. C2 has the second derivative over 2 factorial. C3 has the third derivative over 3 factorial. And so that's really going to be our pattern. Right? If we were to do the derivative one more time, right, what we would see is that C sub 4 is the fourth derivative at a over 4 factorial. We'd see c sub 5 is the fifth derivative at a over 5 factorial. So just as a reminder, right, when we get beyond a third derivative, this is supposed to say c4 here, right? When we get beyond the first derivative, second derivative, and the third derivative, we start to indicate the order of the derivative in a parenthesis. So we would do a superscript with a parenthesis, right? So this is the fourth derivative notationally. This is the fifth derivative notationally. Right? Let me close this gap. Close that gap. So in general, then, what we are going to get is that if I want the nth coefficient, that's not playing nicely for me. I'll ignore it for the moment. This is a Monday for me. Right? If we want the nth coefficient is going to be the nth derivative evaluated at the center divided by n factorial. So what we really have done in this case, let me scroll back up here. What we've really done is we've said if we want a power series, right, here's a power series. Right, if I want a power series for any function, right, the power series for any function, we've just constructed the formula that finds each of those coefficients for ourselves. So these coefficients, the C sub n's, are going to be what we just created. You know, the C0, the C1, the C2, C3, C4, we just generated. So we know the pattern of the C sub n's. Right, so this is going to be the sum of, I'm going to have the nth derivative of the function. We're going to evaluate it at a, and we're going to divide by n factorial, and we're going to have x minus a to the n. So this is what we call a Taylor series. The Taylor series is the formula, if you will, and how we would generate the power series for any function that we want to develop. This is pretty cool, right? So this is the derivation of the formula. This would be the definition of the Taylor series. So let's look at an example, right? Because this is what we're really going to do. So we're going to apply this theoretical concept here. So let's take a look at an example where we look at a particular function and we develop its power series. Okay, so for the example, what I want to do is let's develop the power series for sine of x. So let's use the definition of the Taylor series. To find, let's say, a power series for sine of x. And then just to make this a little easier on ourselves for our calculations, we're going to center it at 0. Okay. So remember our definition was that f of x will have a power series of the form. We're going to take the nth derivative of the function. Now in this case, we're going to center it at 0. And then we're going to have x minus 0 to the n. So look, I'm going to come back and erase this in just a second, right? Because x minus 0 is just x, right? So what I really have is x to the n in this expression. Well, I won't erase it. Let me just write over here. We'll have the nth derivative at the center over n factorial. We'll have x to the n in this case. All right, so how do we manage this? So here's what I'm going to do. I'm going to build a table. And I'm going to organize this information in a table format. Right? So here's what I mean by that. So I'm going to leave that definition up here at the top. Right? I'm going to build a table. So let me build a table. So for each value of n, what I'm going to do is I'm going to find the derivative of the function. So I'm going to find the nth derivative of the function. And then what I'm going to do is I'm going to plug in the center. So I'm going to find the nth derivative at 0 in this case. And then I'm going to take that expression at 0 and I'm going to divide by n factorial. So that's going to be my coefficients. This column will be the coefficients that we have here. So I'm just building up the coefficients here. First I'm finding the derivative for any x. Right here I'm finding the derivative for any x. Then I'm plugging in the center. Then I'm dividing by n factorial. And that's going to be my coefficients. And then the last thing I'll do, this isn't necessary here, but I like to do it all in the same table. Right? And here would be our terms of our series. Okay? So the 0th derivative is just the function itself. So my 0th derivative is just the function I'm developing, sine x. And then I'm going to evaluate that at 0. So I have sine of 0, which is 0. So I technically have 0 over 1 factorial. And remember, 1 factorial is just 1. Right? So I'm really getting 0. So my coefficient is 0, so I have 0 times x to the 0. And that's 0. Right? So the first term in my series is 0. And I'm going to repeat this process over and over and over again. So remember, I need every possible derivative. So I'm going to do the first derivative. So the derivative of sine is cosine. And I know I'm moving a little fast here. Let me stop for a second. Moving a little quick here, so if you need to pause the video or rewind, feel free to do that. Right? So I have the first derivative. The first derivative of sine is cosine. I'm going to evaluate that at 0. Cosine of 0 is 1. So I'm going to do that number divide by n factorial. Right? So remember, my n is 1. So I'm going to take this number. I'm going to divide by 1 factorial. Ooh, and I just called a mistake here. This is 1. All right, I apologize. Up here in the first row, I was dividing by n factorial. N was 0, right? So that would be 0 factorial. I think I said right here 0 factorial was 1, but that's not what I wrote. All right, so back to this line. So when n is 1, we took the first derivative. We took the first derivative, plugged in the center. Then we took that number and divided by the n factorial. So we simplify that. That's just 1 in this case. So I get 1 times x to the 1. That's a times. So x is the second term in my series. I'm going to repeat this until I can see a pattern. So I'm going to do the second derivative. So the derivative of cosine is negative sine. And then I have negative sine of 0, which is just 0. And then I have 0 over 2 factorial, which is just 0. So I get 0 times x squared, which is just 0. Okay. I'm kind of starting to see a pattern here, but I'm gonna do a couple more terms just so I can be 100% sure of my pattern. Right? So let's do a couple more. So I'm going to do n equals 3. So the derivative of negative sine is negative cosine. And look, I'm going to stop writing this here. I'm plugging 0 in. So cosine of 0 is 1, so I get negative 1. And then I have negative 1 over 3 factorial. Right? That was my n expression here. N was 3. Now I'm going to not simplify the factorial. I'm going to leave it as a factorial because that'll help us see the pattern. So typically, we don't want to simplify the factorial. Right? That'll hide the pattern for me. Now notice we kind of can see the pattern here, right? So the x to the 0 term is actually gone, right? The x to the 1 term is x. The x squared is gone. The x cubed is over 3 factorial. So let's see if that pattern continues. When I do the fourth derivative, the derivative of negative cosine is back to sine. I'm going to plug in 0. Sine of 0 is 0. So I'm going to get 0 over 4 factorial, which is 0. So I'm going to get 0 times x to the 4th, which is 0. Right? So we can see every time I have an even exponent, I'm getting 0. And then when I have an odd exponent, right? So the derivative of sine is cosine. Cosine of 0 is 1. I'm going to get 1 over 5 factorial. So I'm going to have 1 over 5 factorial x to the 5th. So we could definitely start to see the pattern here, right? We only have odd exponents that survive, and the exponent is being divided by 1 factorial, right? Or the exponent factorial. The cube is divided by 3 factorial. The 5 is divided by 5 factorial. So there's my pattern. So what I'm going to do is I'm going to pull this off, and I'm going to write this as my function, right? So in other words, I'm going to take sine of x, and I'm going to say that's equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. So what do we think the next term would be? And the next term, notice we're alternating. Positive, negative, positive. The next one would be negative. And look, if that's not obvious to you, we could keep going in our table up here. We could do n equals 6, we could do n equals 7, and we could make sure we're comfortable with the pattern. My next term would be x to the 9th over 9 factorial, and then x to the 11th over 11 factorial. All right, so what's the pattern? We want to write this in sigma notation. Now for the sine series, here's what we're going to do. Right? This is a little interesting, but what we typically don't do is we don't say, n is odd. Right? When I do, let me come down here for a second. When I write sigma notation, I don't say, n equals 0 to infinity, n is odd. Right? I don't do that. The n, the delta n, if you will, is 1. So I really want to go n equals 0, n equals 1, n equals 2, n equals 3, so on and so forth. So I'm gonna consider this the 0 term. I'm going to readjust my index just so I can match the convention that the n value in our series increases one at a time. So there's my n equals 0 term, n equals 1, n equals 2, n equals 3, n equals 4, right? So notice that we have odd exponents only, and we have that same exponent in the denominator, right? So remember, every odd number can be represented as 2n plus 1, right? And then we would have divided by 2n plus 1 factorial. So there would be the terms of my power series for sine of x. Here is sine of x. All right, now look, we could plug the n values back in and make sure we are matching what we have above this. So if I plug in n equals 0, I'm going to get x to the 1 over 1 factorial, and there's my first term when n is 0. If I plug in n equals 1, I'm going to get x cubed, right? 2 plus 1 is 3 over 3 factorial. There's that expression. If I plug in n equals 2, I'm going to get x to the 4 plus 1, which is x to the 5th, right? So on and so forth. So this is the power series for sine. All right, that is so cool. I love this. So the concept here for a Taylor series, right, is basically which functions have a power series. And the answer is every single function has a power series. It doesn't matter what function you look at. We could look at ln of x, that has a power series. We could look at e to the x, that has a power series. We could look at tangent of x, that has a power series. We could look at inverse tangent of x, that has a power series, right? So every single function has a power series representation. It's really, really cool. This is really powerful. So we can use a series to estimate a function. And we'll talk about that in a minute. And I just want to point out to you, right, the infinite summation is exactly equal to the function. But we could use the first 5 terms to estimate the function. And that's what we'll do in an application shortly, right? So the infinite sum exactly equals the function, and then the first 4 terms, first 5 terms, first 10 terms estimates the function. So here's an example of what the Taylor series definition does for me. It generates the function form. Now, this is not how we typically write it, but before we began this conversation, we said that it's the coefficients, the c sub n's, that determine the behavior of my series. So for this example, the c sub n's are 1 over 2n plus 1. Right, for this example, that's 1 over 3 factorial, 1 over 5 factorial, 1 over 7 factorial. Ooh, hang on. I got a mistake here. Right, this is an alternating series. I need an alternating term here. There's my alternating term, right? So when n equals 0, I get negative 1 to the 0, which is positive x. When n equals 1, I get negative 1 to the 1, which is negative the x cubed. So I forgot my negative 1 to the n term. Right? So for the sine function, here's the coefficients. The coefficients are negative 1 to the n over 2n plus 1 factorial. Right? Now if I go back to Stewart's textbook real quick, right, we can see here are the coefficients for this particular function. And for this particular function, here was its coefficients. And for this particular function, here was its coefficients. Here it is, right here, negative 1 to the n, right? So every single function has a power series representation. How do we find that power series? We utilize what we call the Taylor series. What is a Taylor series? It is just a formula, if you will. It's a process, an algorithm by which we can find the coefficients for our function that we're estimating, or well, we're finding the series that's exact. So let me scroll back up for a second. Right, here's our formula for finding that Taylor series. Right? We're taking the nth derivative of the function, we're evaluating it at the center, and we're dividing by n factorial. And the way that I like to do this is I like to organize all of that work into a table. I think that's the most simple way to organize. All right, now something we would typically see in, let's say, a section prior. Right? So I'm using the Stewart textbook here, and this conversation comes from 1110. So usually in the prior section, 11.9, what we did in the prior video, right? Most textbooks usually present this conversation in the same order as Stewart. What we talk about is we can actually differentiate a function to generate a new power series, right? Based on a known series. So we're considering this power series here as a known series, right? We could look at it in this manner. I'm considering this power series to be the known series for sine of x. So what if I wanted to find the power series for cosine of x? Right? So let's say as an example here, right, we want to find the power series for cosine of x using, let's say, the known series that we just built for cosine of x. All right, so, oops, goodness gracious, it is Monday and I am writing so many typos. The known series is sine of x. So we're just built a formula, the known series for sine of x, and we want to use that to find a series for cosine of x. So the simplest connection here is to say, well, how do I go from my known series to the one we're trying to find? And it's a derivative. Right? So we know that the derivative of sine is cosine. So let's write out the series for sine. Right? So I have sine of x is, I'm going to write out the first couple terms, right? X cubed over 3 factorial plus x to the 5th over 5 factorial. My digital pen and my hand and my brain are not working together today. Right? So then we have minus x to the 7th over 7 factorial plus blah, blah, blah. Right? Let me just say plus blah, blah, blah. And so that is equal to the sum of negative 1 to the n over 2n plus 1 factorial x to the 2n plus 1. Right? There's our closed sigma form, right, as n goes from 0 to infinity. All right, so we are making the connection that if I differentiate sine, I get cosine. So that's the series we're looking for. We're looking for the series cosine. And if we differentiate sine, we get that series. So I'm going to differentiate the left-hand side, right? I'm going to take the derivative of sine. And then I'm going to take the derivative of this guy. All right, look, I don't want to have to rewrite all of this. So I'm going to say, in red, right? In red, I'm being lazy. I'm going to take the derivative of all of that stuff. Okay. Now, so also when I differentiate that series, right? This is the series as what, let me call it an expanded form. So there's the derivative in an expanded form. I'm could also take the derivative of the sigma notation. So I could take the derivative of the series in this closed sigma form. And I want to talk about doing that as well through this little conversation here. Right. So again, I'm going to use red brackets, right? So this guy is what I'm taking the derivative of here. Okay. Right. Okay, so how would we go through that process? So here's what we would do. Right? So if we look up at this first line that we wrote right here, here's our first line. We have the expanded form. When we differentiate that, right, we're differentiating x, we're differentiating x cubed, we're differentiating x to the fifth, we're differentiating x to the seventh, right? So we know that the derivative of a sum is the sum of the derivatives. So I know that derivative of sine is cosine of x. So the derivative of x is 1. And then this derivative, right, I'm really only looking at, right, 1 over 3 factorial is a constant. So I'm differentiating x cubed, which is 3x squared. Right? And then 1 over 5 factorial is a constant, so I'm going to pull that out. And then I really have 5x to the fourth. And then let me go ahead and do the next one, right? 1 over 7 factorial is the constant, and then I have 7x to the sixth plus dot, dot, dot. Now, how do I differentiate the sigma notation? Well, think about this for a second. What does the sigma really represent? It really represents the plus, minus that we have in the expanded form. That's all the sigma really represents for me. So I can take the derivative and I can push it over the plus and minus signs, right? The derivative of sum is the sum of the derivatives. So technically, right, I can push the derivative, I can pull the constants off. Remember, all of these denominators were just constants that we pulled off, and we're going to differentiate x to the 2n plus 1. That's what we're differentiating here. So if I take the derivative of x to the 2n plus 1, how do I manage that? Well, we just did that. How did I take the derivative? Let me scroll back up, right? How did I take the derivative of x cubed? I took the power down and took 1 away. Uh-oh, I didn't write that. Oh, yeah, here it is. I wrote it, right? So I took the power down, subtracted 1. This was x to the fifth up here. How did I take the derivative? Brought the power down, took 1 away. X to the seventh. How did I take the derivative? Took the power down, take 1 away. So when I write this term over here, how do I take the derivative? Well, I'm going to bring the power down, and then I'm going to take 1 away. So in the closed sigma form, there's my derivative. Right, you know, I've been getting sloppy and lazy. This is from 0 to infinity. Right? So all of these terms that we have right here, right, the expression for cosine, our infinite polynomial for cosine, if you will, right, our Taylor series for cosine, here is what those terms look like in sigma form. Now we could do a little bit of cleanup. Go with me here. Right? So if I look at this expression, notice the 3 and the 3 factorial look like they might be able to cancel. So they don't really cancel, right? Here's what would I do to simplify that. So the 3 is in the numerator. And then 3 factorial, in order to get those 3's to cancel, I'm going to write this as 3 times, 2 times 1. Right? And then I have the x squared. So this is really 1 minus. The 3's cancel, and I really have 2 factorial in the denominator. And I can play that same game with the next term. So this next term, I have 5 in the numerator, 5 factorial in the denominator. So I have 5 in the numerator. And then the 5 factorial I could write as 5 times 4 times 3 times 2 times 1, right? Or 5 times 4 factorial. So the 5's cancel, and I get 1 over 4 factorial, x to the 4. And then my last one, my lines are getting a little off kilter here. And the next one, right, the 7 is in the numerator, so I'm going to have 7 over, and then the 7 factorial, I'm going to write as 7 times 6 factorial, x to the 6. So that's minus the 7's cancel. I got 1 over 6 factorial, x to the 6th. So that's equal to this guy here. So how do we simplify this expression? I got a little wonky here. I apologize. with my notation. So how do I simplify this expression here? Well, I'm gonna do the same process, right? So the numerator and the denominator canceled. The first number canceled. I want to be careful how I say that, right? So in the denominator I took 7 factorial. I pulled the 7 off and wrote the rest as 6 factorial. So in the denominator here, I'm going to take the 2n plus 1 off, and I'm going to have 2n factorial left over. I still got the negative 1 to the n. And then this 2n plus 1, I'm just going to pull to the numerator. And then I have the x to the 2n. Right? So that's what my new simplified version looks like. And we can see the 2n plus 1s are going to cancel here. So I'm really just going to end up with negative 1 to the n over 2n factorial. That's what's going to survive, if you will, right? So I'm going to have negative 1 to the n over 2n factorial and x to the 2n. And that's exactly what we have right here, right? Here's what we have. So we have cosine of x equaling all of this stuff. Here's cosine of x right here. We got 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, right? Minus x to the 6th over 6 factorial plus dot, dot, dot. And n goes from 0 to infinity. So here's our power series for cosine. Our power series for cosine is this form in sigma notation, and here would be my expanded version. And if we look at this pattern, right, these are all even exponents. This is x to the 0, this is x squared, x to the 4th, x to the 6th, and then I have the same denominator. So any even number is x to the 2n. Right? So x to the 2n. Any multiple of 2 is an even number. So there's all of my even numbers as n goes from 0 to infinity. Isn't that cool? Oh man, that is so cool. All right, so given a known series, like sine x, I could take the derivative and create a series for cosine. Now here's the advantage to this. The advantage to this in particular is I don't have to go through that really long-winded process that we just did for sine. Right, so for the sine series, we built this huge table. We took all these derivatives. We plugged in the center. We generated every term of the series. That was lengthy. It was awesome, right? But it was lengthy. So now that we have that known series we generated, then we could do a derivative, or we could do an integral of the series. So, you know, for example, if I had the series for 1 over 1 minus x, I could integrate that and create a series for ln of x, without having to go through that long-winded process. So in this section for this textbook, what we just did is not really part of this section. It would be the prior section that we did in the prior video, taking derivatives of known series, taking integrals of known series. Okay? So the Taylor series, that whole tablature process of building the coefficients, is really what we're talking about in 11.2. Now these are long-winded, right? They're lengthy, so I don't want to do any other examples. This video is already 40 minutes. I don't want this to be 2 hours. Now I want to do a couple more problems where we use this known series for cosine and we develop some other series. So next example. So in some of the applications, what we're going to want to do is use a power series to estimate a function. Right? So I want to do an integral, right, of something in particular. You know what? I don't want to do this one yet. Hang on. Let me backtrack for a second. So let's say what we want to do is create a series. So let's develop a series. Let's find a power series for f of x equals cosine of x squared. Right? All right, so we know the power series for cosine. We just developed that guy. It's negative 1 to the n over negative 1 to the n over 2n factorial x to the 2n. There's our power series for cosine x. Now we're asking what's the connection to cosine of x squared. How do I make that connection? Well, really, cosine of x squared is just a substitution. And here's what I mean by that. Let me come back to the cosine function. We're using x as the variable, but I could use any letter that I want, or whatever the domain is. Right? If I'm thinking of the input as an angle measure, then I could call this theta. Right? Cosine of theta would be -1 to the n over 2n factorial theta to the 2n. Right? I could think of this as cosine of u. Cosine of u is -1 to the n over 2n factorial u to the 2n. Cosine of blah is -1 to the n over 2n factorial blah to the 2n. Right? Cosine of smiley face is -1 to the n over 2n factorial smiley face to the 2n. So the letter we're using here doesn't really matter. So when I look at cosine of x squared, I'm thinking of x squared as the theta, or x squared as the u. Or x squared is my smiley face, right? So I'm literally going to take my u variable and I'm going to plug it into my variable here. So I'm just going to do like an algebraic substitution in this case. So I'm going to have -1 to the n over 2n factorial, and my variable of, let's say, u is u to the 2n. In this case, my u is x squared. So I have x squared to the 2n, and there's my power series for cosine of x squared. We're just doing an algebraic manipulation there. So, all right, I could simplify this. This is -1 to the n over 2n factorial. And so when I multiply exponents in this case, right, x to the 4n. So there's my power series for cosine of x squared. I love this stuff. Isn't that cool? All right, so last one. Let's say we look at x squared times cosine of x squared. So we want to create a power series for this guy. I'm gonna get a little lazy. Time on this video is getting a little long. So instead of writing the instructions, right, the instructions would be find a power series for this function, f of x equals x squared cosine x squared. And we're going to use the series we just developed. We just developed the series for cosine x squared. And again, the reason I'm using the prior known series is I don't really want to have to go through the definition of the Taylor series, building that big table. So if I have the advantage of using a prior known series, I want to take that path that's more efficient. If I had to, I could do the Taylor series definition and build through that whole table. But in this case, we don't have to, right, in the example I'm doing here. All right, so in this case, now we're just multiplying our known series. So we're taking the series that we have for cosine, which is this guy here, -1 to the n, 2n factorial, x to the 4n. We're just taking that power series and we're multiplying by x squared. So when I multiply, what do I do with that, x squared? Well, I'm just really distributing, right? What does this sigma notation represent? It represents a bunch of plus signs. So when I just have x squared times a plus b, I distribute the x squared to the a and the b. So I'm just pushing the x squared over all of the addition symbols. So I'm just pushing the x squared through the plus signs. There's the plus signs, right? So this becomes x to the 4n plus 2. So my power series becomes -1 to the n over 2n factorial x to the 4n plus 2. And this is the series for x squared cosine of x squared. Right? All right, so let me stop there for a moment, and I want to look at an application. All right, so here's an application that I want to look at here. So we have the function we just developed. We have f of x equals x squared cosine of x squared. And we could, in some scenarios, utilize this function to represent a periodic behavior where the amplitude grows, right? So we can see in this graph, here's the graph of f of x equals x squared times cosine of x squared. So again, we see periodic behavior where the amplitude is increasing. But in this case, the amplitude is x squared, right? And so that's variable, it's growing. Now we could consider the fact that the integral of that function is going to calculate the power needed to generate the wave. So we want to integrate. Where are you going, mister? We want to integrate x squared cosine of x squared. All right, now for just a moment, if we look at this, notice that we can't use any technique of integration that we already know. We actually could not use by parts on this integral. Feel free to try, but we could not use by parts on that integral. We couldn't use any technique at all that we already know. We could not use U substitution. We could not use, trig substitution. We couldn't use any technique. So the only way we could really evaluate this integral is to estimate it. So we're going to use the power series that we have for this function, and we're going to estimate its value. Now, technically, the series that we had was -1 to the n over 2n factorial x to the 4n plus 2. So just like we did with the derivative, we pushed the derivative through the plus or minus signs. We could do the same with the integral. We could push the integral over the plus and minus signs, which is the sigma notation. All right, so we're using the property of integrals to evaluate the integral of this series and thus the integral of our function. So again, I'm using the property of integrals to push the integral through the summation symbol. Again, summation symbol is just a bunch of plus and minus signs. So all I'm integrating is my x variable. So simple enough. When I integrate an x power, what do I do? Right? So think about this. If I integrate x cubed, what do? I add 1 to the power and I divide by that new power. Right? So when I'm integrating x to the 4n plus 2, what am I going to do? So I'm going to add 1 to the power and divide by the new power. So in this closed form that we have here, I'm going to add 1 to this power. So when I add 1 to this power, I get 4n plus 3. And then I divide by 4n plus 3. And there's my integrated form. So that integrated form represents x squared times cosine x squared integral. Let me scroll back up a second, right? So this integral, the integral of this function, will equal the integral of its series. We did the integral of the series. So here's the integral of x squared cosine x squared. Isn't that cool? This is so cool. All right, so keep in mind what we're doing. Remember, this is just a polynomial. This is an infinite polynomial. So we're using a polynomial to estimate a function. Well, all right, hang on. This is exactly equal because we have the infinite series. Right? But if we use the first 5 terms, it's an estimation. So let's do that real quick. Let's use the first 5 terms of this series to estimate the integral. So let's do this. Let's use the first 5 terms to estimate the integral. All right, so again, we're saying the integral of x squared cosine x squared will now be approximately equal to, oops, let me put the dx there just for thoroughness. So this is approximately equal to the sum of the first 5 terms. Now think about it for this scenario. The first 5 terms would be from 0 to 4, right? Because we started 0. So 0, 1, 2, 3, 4 gives me the first 5 terms. So I'm looking at just the first 5 terms of this series that we just found, the integral So I'm going to plug in n equals 0. I'm going to plug in n equals 1, 2, 3, 4, and 5. So let me see if I can squeeze all this on one line. So the integral of x squared cosine of x squared will be approximately. So when I plug in n equals 0, I'm going to get negative 1 to the 0, which is positive 1. I'm going to get 2 times 1 factorial, which is just 2. Oh, goodness gracious. I'm plugging in n equals 0. Come on. Plugging in n equals 0. So that's 0 factorial, which is 1. And then I have 4 times 0 plus 3. And then x to the 0 plus 3. There's x cubed in the numerator. All right, now when I plug in n equals 1, I'm going to get negative 1 to the 1, which is a minus. And then I'm going to have in the denominator 2 times 1 factorial, which is 2 factorial. And then when I plug 1 in here, I'm going to get 4 plus 1, which is 7. So 2 factorial times 7. And then I'm going to have x to the 7 from the variable. So there's my first two terms. I'm going to say plus. So when I plug in n equals 2, I'm going to get negative 1 squared, which is positive. I'm going to get 2 times 2, which is 4 factorial. And then that's going to multiply. So when I plug in n equals 2, I'm going to get 8 plus 1, which is 11. So I have x to the 11. So there's the first three terms. The first four terms would be, let's see, I'm plugging in n equals 3. So I'm going to get negative 1 cubed, which is negative. And then I'm going to get 2 times 3, which is 6 factorial. And then times, when I plug in 3 here, I'm going to get 12 plus 3, which is 15. And then x to the 15. You know what, let me do this because I'm out of paper. So I'm going to cheat. Let's use the first four terms. Let's use the first four terms. So if I use the first four terms, I'm going from 0, 1, 2, and 3. So I'm using the first four terms. There's my first four terms. All right. So the first four terms of that series gives me an estimation to the integral of that function. Now, you know, a legitimate question here is, well, why would we approximate? Well, think back to the wave question that we had, right? Let me see if I can scroll back real quick. Right? The wave question that we were looking at, right, is that the wave is, when I integrate the wave, that gives me the power. So let's suppose that the horizontal axis is time. So this wave has growing amplitude over time, right? Now, if this was a tidal wave, you know, the amplitude isn't going to grow forever and ever and ever. Let's assume, right, and I'm just picking kind of random values here, right? But let's assume that there's seismic activity, there's an earthquake, a wave is generated, and let's say, you know, it really only takes the first 3 minutes for the wave to reach its maximum amplitude. So in that case, we would integrate from 0 to 3. So if I'm integrating from 0 minutes to 3 minutes, then I don't want the infinite series, right? How can I plug 0 to 3 minutes into my infinite series? That's insane. I got infinitely many terms. So we're going to use the first four terms, and we would evaluate that from 0 to 3. Right? So we would say this, I'm going to evaluate from 0 to 3 minutes. Right? That's, remember, I'm talking about minutes there. Right? So if I integrate from 0 minutes to 3 minutes to find the power needed to generate that tidal wave, then I'm integrating from 0 to 3. So I'm taking my antiderivative, I'm plugging in 3, and then I'm going to subtract, plugging in 0, and that's going to give me a numerical estimation. So, all right, so let's find, last example, right? Let's find. Now, actually, what we're finding is a Maclaurin series. Now, let me talk about what that is in just a moment. But let's find the Maclaurin series. So this is centered at 0. This is centered at 0. For e to the x. Let's do e to the x. So let me stop for just a second. What is a Maclaurin series? All right, so I've pulled up Stewart's book here, and this was the formula right here, Formula 6, in this beautiful blue box. This was the formula for the Taylor series. So it is centered at any number a. So if we want to center the series at x equals 3, we could do that. Right? Now, the Maclaurin series is what we call the Taylor series centered at 0. So most scenarios, the most simple aspect of finding a power series is to center it at 0. And we definitely could center the series anyplace else. If we center the series at any number non-zero, we technically call it a Taylor series. And if we plug in a equals 0, we're going to officially call this a Maclaurin series. So Maclaurin series is a Taylor series. It's just a Taylor series centered at 0. Now before we go off and do this example here, I want to come back and look visually at our Sine series. Alright, so what I did is I brought up a web browser and I've gone to Desmos.com. And what I want to do in this example is I want to look at our Sine series. So let me minimize this browser for a moment. And I want to look at the Sine series. So again, I want to point out to you here I'm at Desmos.com. And I want to graph the Sine series. So one thing I can do, in the upper left hand corner, Desmos has a bunch of pre-written examples. And I'm going to scroll down and I'm going to pull up the Taylor expansion and let me open this graph. Right. So here's the graph that I want to look at. I want to look at the graph for sine of x. And here's what it's done. It's plugged in the Taylor series, which is really the Maclaurin series. They centered this at 0. So here's my sine function that I'm graphing in red. All right. So remember, the Taylor series, the Maclaurin series in this case, is an expression that can approximate the function. So if I turn that graph back on, here is the very first term in that series. This is x. I remember when we plug in equals 0, we got x as the power series. Right, here's our power series. So the 0th term, right, the first term, is y equals x. And if we come back to this graph, we can see that here's y equals x. And near the center, the convergence is, the estimation is really, really good. The further away I get from the center, if I'm out here at x equals 4, the estimation of the series, y equals x, is horribly off from the sine function. So if I only look at the first term, the estimation lives in an interval relatively small, and it's centered at x equals 0. And if I add the first two terms, here's the first two terms of the series, and if I go back to my notes, the first two terms of the series is a cubic expression. So if I come down to my graph again, here's the cubic function, and notice the convergence spread further away. Right? Let me go back. Here the convergence looks like it's only good between, let's say, about -1 to 1, and then when I add the second term, the convergence is good. It looks like about 1.5 to 1.5. So and then when I add the next term, here's the 5th degree polynomial. This looks good from -2 to 2. When I add the next term, here's the 7th degree polynomial, the 9th degree, the 11th, so on and so forth. So we can see in this scenario that as I add more and more terms, the convergence spreads, and notice that the convergence is always centered at 0. So every time we find a power series, the concept is we're estimating this function. Again, the infinite series exactly equals the function. The first 10 terms estimates the function. Now, in a prior section, we discussed intervals of convergence. So for the sine series, the interval of convergence is -infinity to infinity. So if we kept adding more and more terms, we're going to see the convergence spread all the way out to infinities in the positive and negative direction. So what that means is the estimations will be valid in large intervals. Now what I'm going to do up here is let me turn this guy off. And one of the prior known series that we looked at was 1 divided by 1 minus x. This was the geometric series. And the geometric series that we got there was x to the n. So let me delete all of this stuff. Alright, so here's the function 1 over 1 minus x. Here is its power series. And what I'm going to do with that power series, let me turn it back on, I'm going to add a term at a time. So notice as I add the next term and the next term and the next term, the convergence is spreading from the center. Again, notice this is a Maclaurin series centered at 0. So the convergence is spreading from the center. Now, in the prior video, we had used the ratio test to determine the interval of convergence, and we noticed that the interval of convergence was only good between -1 to 1. So notice, no matter how many terms I add here, the convergence is only good between -1 to 1. So the sine series kept spreading through all reals, but for 1 over 1 minus x, it doesn't. It's only good between -1 to 1. So I can't, so let's say I'm integrating this power series. I cannot look outside -1 to 1. If I integrate from -4 to -2, this is a horrible estimation because the series is divergent there. So we always want to only look in the interval of convergence. All right, so I got a little sidetracked there. I went off on a tangent, pun intended, right? So a Taylor series is centered at A. So if I center the series at 0, the convergence spreads from there. Right, let me go back to this example. If I center the series at 0, the convergence spreads from there. If I center the series somewhere else, then that's where it's going to spread from. So I paused the video real quick, and I came in and I plugged in x minus 3 to both expressions. So instead of the Maclaurin series centered at 0, I've used the Taylor series centered at 3. So I shifted my sine function over 3 units, right? And we can see the first term. Notice the convergence is going to start at the center at 3. And as I add more and more terms, that convergence is going to spread from that center. So that's the significance of the center. So when I come back to other power series, I might want to be able to integrate from -4 to -2, and so I would need to shift my series to to converge in that interval. All right, so I got a little sidetracked there, right? I introduced the concept of Maclaurin series. That's a Taylor series centered at 0. And then I just wanted to show visually what does it mean to converge, right? What's the significance of the center? The center is where the convergence begins, and it spreads from there. So let's come back and let's find the series for e to the x, and we're going to use the definition. So again, let me remind ourselves of the definition, right? The definition in this case of the Maclaurin series is going to be the sum of, so all of my coefficients are the nth derivative of the function evaluated at the center over n factorial x minus 0 to the n. So we're going to have n going from 0 to infinity, right? So again, we're creating these coefficients. That's what we want to generate. So I'm using the e to the x function, right? So I'm going to have, the values of n that we're going to look at. And then we're going to build those coefficients. So I'm going to first find the nth derivative of the function in general. And then I'm going to find the nth derivative of the function evaluated at 0. And I'm just going to save a little time and go ahead and divide by n factorial as well. And then I'm going to multiply by my x to the n. So I'm going to take that coefficient, divide by n factorial, and multiply by x to the n. So if I start at n equals 0, that's the original function. That's the 0th derivative. And then when I plug 0 into that, I get e to the 0. And I'm going to divide by 0 factorial. So anything to the 0 power is 1. 0 factorial is 1. So my first coefficient is 1 times x to the 0. Right? So that's just 1. First term is 1. Now when I plug in n equals 1, I want the first derivative. So when I look at the function e to the x, the first derivative is e to the x. So then I'm going to plug 0 into that, and I'm going to divide by 1 factorial. So that's really, 1 over 1 factorial. That's 1. So I get 1 times x is my term. So then if I do n equals 2, I'm taking the derivative of the first derivative, that's e to the x. So I'm really getting e to the 0 over 2 factorial. So I'm going to have 1 over 2 factorial x squared. There's my next term. Let's do a couple more terms. I think I can already start to see the pattern here. Let me do the third derivative. So that would be the derivative of the second derivative. And then I'm going to have e to the 0 over 3 factorial. Right? E to the 0 is 1. So I have 1 over 3 factorial x cubed. So it looks like the pattern is for each n, I'm going to have x to the n over n factorial. X to the n over n factorial, x to the n over n factorial. Let's just do one more to make sure that we're looking at that correct. So the fourth derivative is the derivative of the third derivative. I'm going to plug in 0, divide by 4 factorial. So that's really 1 over 4 factorial x to the fourth. Right? So that definitely is my pattern. So if I write the terms out here, right, I'm going to have e to the x was 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot dot dot, and that's equaling x to the n over n factorial, as n goes from 0 to infinity. All right, awesome. So there's our Maclaurin series because it's centered at 0. Now, if we scroll back up to our example of sine, right, which I don't want to do. This Word doc is such a pain, right? So if I scroll back up to sine, remember with the sine function, every other term was 0, and so I readjusted the index. So I wrote the terms and then I readjusted the index. But I don't need to do that here. I don't have 0 in any of my terms. So this is the n equals 0 term, n equals 1 term, n equals 2 term, n equals 3 term. So just like the sine series illustrated, if you get zeros as your term, then you need to readjust your index, your n values. And in this case, we didn't get that result. Now technically, to find the interval of convergence, I would need to do the ratio test here to find that interval. So let's go ahead and do that as the last part of this example. Let's find the interval of convergence. Right? Now remember, in our prior video, which was 11.8 in Stewart's textbook, we used the ratio test to find intervals of convergence. So I'm going to use the ratio test here. I'm going to take the limit of a sub n plus 1 over a sub n, and that's my ratio test, right, as n goes to infinity. So for this series, I have, let me scroll back up so we can see it. Right, here's my power series here, x to the n over n factorial. So I'm going to have x to the n plus 1 over n plus 1 factorial, and that's going to all be divided by the nth term, x to the n over n factorial. And that's the limit as n goes to infinity. Right? So I'm going to flip and multiply. Now remember, the beauty of the ratio test is, factorials clean up really nice, exponentials clean up really nice. So we did this in 11.8. So I'm going to break up the exponential term. This is x to the n times x to the 1 over n plus 1 factorial. And then I'm going to flip and multiply this denominator. That's going to be n factorial over x to the n. And again, the advantage here is with the exponential term, the x to the n's are going to cancel out there. So I'm going to get the x to the n's canceling. And I basically have, in this case, n factorial over n plus 1 factorial, x. Right? So again, the x to the n's canceled, and just the x to the first survives, if you will. Right? So then, remember, the other beautiful aspect of the ratio test is the factorials will clean up really nice. So I'm going to have, what am I going to have? I'm going to have the limit of, let me pull the x here for the moment, right? So I'm going to have n factorial, and then the n plus 1 factorial we're going to write as n plus 1 times n factorial. The n factorials cancel. So I'm going to go ahead and pull the x out. So remember, when we did the ratio test, we talked about that was completely legitimate to do, because the limit process is only looking at the n expression, right? My limit process is only looking at the n. My x variable doesn't have any n's like in the exponent, right? So this is x to the first. I can pull x to the first out. I'm just going to make sure I keep it in the absolute value symbol. So then we evaluate this limit. Right? So 1 over infinity, if you will, goes to 0. So we end up with absolute value of x times 0. Now remember, for the ratio test, we show convergence by this limit being less than 1. So technically, we're asking, when is that limit less than 1? When the limit is less than 1, we get convergence by the ratio test. If that limit equals 1, there's no conclusion. If that limit is greater than 1, it's divergent. We don't care where the series diverges. We only care where the series is convergent. So we set the limit to be less than 1. So in this scenario, we have something pretty interesting. We have absolute value of x times 0 less than 1. So what values of x will make this less than 1? And it would be any value, right? If I pick x equals 3, I get 3 times 0, which is 0. That's less than 1. If I pick x equals negative 18, I'm going to get negative 18 absolute value. Positive 18 times 0 is less than 1. If I pick x equals 1,468, that times 0 is less than 1. Right? So any x I pick is going to be less than 1. So we have our interval of convergence. My interval of convergence is going to be minus infinity to infinity. Right? So all reals. Right? We could write that as minus infinity to infinity in interval notation. We could just say all reals, right? There's my interval of convergence. And then we can say the radius of convergence is infinite. Okay. All right, so that's the last piece I wanted to do. This video is already long enough. There is 11.10 in Stewart's textbook. This is Maclaurin Series and Taylor Series. Hope you enjoyed the video. I will see you in the next video.